Welcome to Scale Up University. Welcome to the course on fluid mechanics. So this is the lecture 1 of module 1. So in this lecture we'll discuss scope of fluid mechanics. So we'll talk about what is fluid mechanics, why is fluid mechanics important, scope of fluid mechanics, the triad approach to fluid mechanics, career applications, software tools overview, big picture takeaway. So all these topics we will discuss in this lecture itself one by one. So this is the module 1 introduction, lecture 1 scope of fluid mechanics, and we are starting with the first topic of this lecture, that is what is fluid mechanics. So if we talk about the definition of fluid mechanics, so basically fluid mechanics is a branch of mechanics that studies the behavior of fluids, that is liquids and gases, at rest and in motion. So fluid mechanics is a branch of mechanics studying behavior of fluids, that is liquids and gases, at rest and in motion. So if we talk about a fluid, so a fluid is something which cannot sustain shear stress at rest, because when you apply a shear stress on it, it will displace. It cannot sustain shear stress. So that is fluid. So whenever a shear stress is applied, it will undergo deformation. So it deforms continuously under any applied shear stress. So liquids and gases, they are fluids, because when you apply shear stress to fluids and gases, they undergo deformation. Continuously they will keep on deforming, and hence they are fluids. And fluid mechanics, as the name suggests, fluid mechanics, it's the branch of mechanics studying behavior of fluids at rest and in motion. So we have two major divisions in fluid mechanics. So we have fluid statistics, which deals with the study of fluids at rest, and we also have fluid dynamics, which deals with study of fluids in motion. So fluids in motion is fluid dynamics, fluids at rest is fluid statics. Now later in the course, these uh, uh, divisions, it will further expand, like because in the later part of the course you will see we will start talking about internal flows, wherein the fluid is flowing internally in a system like pipes and ducts. So internal flows. We'll talk about external flows, wherein the fluid, they will flow externally, like in aircraft and vehicles. Compressible flows, high speed aerodynamics, open channel flows across rivers and canals, and turbo machinery, like the pumps and turbines. So all this we will cover in this course itself. So these are like further extensions of fluid mechanics, wherein we will be studying internal flows, external flows, compressible flows, open channel flows, turbo machinery in this course itself. Why is fluid mechanics important? Now, if we talk about Earth, so the Earth, 75% of it is covered by water, and 100% of it is covered by air. So the Earth, it in itself is surrounded by the fluid, because water and air both are fluid. So 75% of it is covered by water, 100% of it is covered by air. So this means nearly every engineering system interacts with a fluid. So that's why fluid mechanics is very important, because nearly every engineering system, it interacts with a fluid. Fluid mechanics affects weather systems, ocean currents, aircraft flight, ship stability, energy production, blood circulation, industrial processes, environmental systems. So in all these areas, fluid mechanics has a role to play in weather systems, ocean currents, aircraft flight, ship stability, energy production, blood circulation, industrial processes, environmental systems, fluid mechanics plays a role. So we can say that fluid mechanics, it is not a niche subject, rather it's a foundational subject. It is a very important foundation which directly affects so many different fields. So that's why fluid mechanics is very important for us to master. Scope of fluid mechanics. Now, fluid mechanics has got a lot of scope in different fields, like in meteorology, fluid mechanics, it studies atmospheric flows, wind patterns, cyclones and storms, jet streams. So basically, the study of atmospheric flow, wind patterns, cyclones, storms, jet streams, it involves the concepts of fluid mechanics. So what is the role of fluid mechanics? So air is a fluid, air is a compressible fluid, and hence while studying the flow of air, fluid mechanics will come into the picture. We have something called as Navier-Stokes equations, turbulence modeling. So all these are like concepts of fluid mechanics, and they are used heavily in meteorology. If we talk about oceanography, so fluid mechanics play a role in oceanography also, wherein it studies ocean currents. So oceanography, we deal with ocean currents, waves, tides, tsunamis, and fluid mechanics, it has a role in these fields of studies, wherein it helps us in understanding free surface flows, wave theory, buoyancy, and density stratification. And it has got engineering applications as well in offshore platforms, submarine design, and floating wind turbines. Now, fluid mechanics also has got scope in hydrology. Now, hydrology, it deals with or it studies river flow, flood modeling, groundwater flow, and watershed dynamics. And fluid mechanics, it plays a role in studying all this. Like we have open channel flow theory, hydraulic jump, specific energy, flow measurement. So it has got engineering relevance as well, dam design, flood control systems, irrigation networks. So fluid mechanics has got a tremendous scope in hydrology as well. If we talk about aerodynamics, so aerodynamics, it deals with flow over aircraft wings, drag on vehicles, lift generation, supersonic flights. And fluid mechanics role is the boundary layer theory, Bernoulli's equation, compressible flow, shock waves. And it has got tremendous applications in the field of aircraft, rockets, drones, and sports ball design as well. So just look at the scope of fluid mechanics. Like in every field, we are seeing it, fluid mechanics playing a very important role. If we talk about hydrodynamics, there also fluid mechanics has got tremendous scope, wherein hydrodynamics, it deals with the study of flow around ships, submarines, propellers, naval architecture. And the core concepts of fluid mechanics which we can apply in hydrodynamics, the study of hydrodynamics is buoyancy, stability, drag forces, wave resistance. Now, fluid mechanics, it also has got applications, the scope in energy generation, especially the turbines, because in power plants, in energy generation, the rotation of turbines plays a very important role. So fluid mechanics, it powers hydroelectric dams, wind turbines, steam turbines, gas turbines. Their fluid mechanics principles are involved, like conservation of energy, momentum equations, turbo machinery analysis. So nearly all electrical energy generation involves fluid flow. Now, fluid mechanics also has got applications, the scope in combustion. And what role fluid mechanics plays in combustion is, see, combustion involves reacting gases. Now, when the gas react, it is basically mixing of fuel and air. flame stability, turbulent reactive flows. So here fluid mechanics plays a very important role in studying all these concepts. Applications, if we talk about, of combustion, jet engines, power plants, internal combustion engines. So just look at the scope of fluid mechanics. In combustion also, fluid mechanics helps us in analyzing flame stability, turbulent reactive flows, mixing of fuel and air. Like we can perform a systematic study. We can build mathematical models based on the concepts of fluid mechanics, because here also we are dealing with fluid. So wherever we are dealing with fluid mechanics will come into the picture. And whatever we are seeing, meteorology, oceanography, hydrology, aerodynamics, hydrodynamics, energy generation, combustion, here we are dealing with fluid. Even in irrigation, pipelines and flood control, we are dealing with water, the fluid, and hence fluid mechanics has a role to play. So fluid mechanics is central to oil and gas transport, water supply networks, sewer systems, canal design, urban drainage design. So the key concepts of fluid mechanics involved is head loss, friction factor, pump selection, cavitation. So now we are convinced that fluid mechanics is a very important field of study. It is not a niche, but it's like a foundational field of study, because we can realize its importance, its application across several domains. So whenever we are designing an engineering system, we are dealing with fluid mechanics, the triad approach to fluid mechanics. So basically, when we are studying fluid mechanics, we have to keep in mind three approaches. So the first is the integral method. So fluid mechanics, it makes use of integral method. And what are integral methods? What it means, let us first understand that. It means in integral methods, we apply conservation laws over a finite region, control volume. So what we do, rather than analyzing a single particle, we are analyzing a system of particles like a finite region, a controlled volume, and we are analyzing its behavior. So that is the integral method. In integral method, we are applying the laws over a finite region. And here in integral methods, like when we are studying fluid mechanics, we will be following integral method approach, and there we will be talking about conservation of mass of a system, not a particle, linear momentum equation, Bernoulli's equation, energy equation. And studying fluid mechanics from the integral method approach, like if we consider a finite region or a controlled volume, it has got some very interesting advantages we achieve. Like it is like very practical study for system level design. It is used heavily in pipe flow analysis, the integral methods, and it's ideal for pumps, turbines, and jets. So in integral methods, we are analyzing a finite region, how it behaves, and it has got like lots of practical applications. It is used, integral methods are used heavily in pipe flow analysis, system level design, in pumps, turbines, and jets. So that is one of the approach to study fluid mechanics. The second approach is the differential methods. So if we look at what it means, so in differential methods, what we do, we apply conservation laws at a point using calculus. So here, rather than analyzing a system or a finite region, we are analyzing individual points. We are analyzing individual points. So the core equations involved in differential methods are continuity equation, Navier-Stokes equations, energy equations in the differential form. All this we will study as differential methods. And it also has got applications like differential methods. It is used in computational fluid dynamics simulations, boundary layer theory, and turbulence modeling. And differential methods, it forms the theoretical backbone of fluid mechanics. Now we have the third approach, and that is the experimental methods. So in experimental methods, so see, the idea is that fluid mechanics, we cannot like understand it fully just by analytically. Like fluid mechanics cannot be fully solved analytically. Experiments will also play a very important role. So we'll make use of experimental tools. So in experimental methods, we make use of something called as wind tunnels, water channels, flow visualization, like the dye smoke, rheometers, pressure sensors. So we make use of the experimental tools. And why it's important? Because we will be able to like do practicals. The turbulence is complex, empirical correlation is required. We can validate the theory. So with experimental methods, even complex phenomena, we can feel it. We can do a practical of it. Empirical correlations we can establish. And most importantly, we can validate the theory, because by using integral methods and differential methods, whatever theory or observations or whatever analysis we did, we can validate that using experimental methods. So this is the triad approach to fluid mechanics, wherein while studying fluid mechanics, while mastering fluid mechanics, we have to master these three methods. We have to be very good in applying integral methods to fluid mechanics, wherein we will be considering, or we will be analyzing a finite region or a controlled volume. We will be using differential methods to study different fluid mechanics, wherein we'll be analyzing point rather than a system. We'll be analyzing point. And we will also make use of experimental methods to study fluid mechanics, wherein whatever analysis we did, theoretical foundation we built, we will validate that experimentally. We will conduct experiments. We will establish empirical correlations. We will be able to understand complex systems also with experiments. So that's the triad approach to fluid mechanics. Career applications. So fluid mechanics, we already saw the scope of fluid mechanics. So fluid mechanics, it opens door to many different domains like aerospace engineering, mechanical engineering, civil engineering, even environmental engineering, ocean engineering, renewable energy, research, that is computational fluid dynamics, turbulence. Even in space technology, fluid mechanics plays a very important role. Oil and gas, because oil, gas, they are fluids. Even in defense sector, fluid mechanics has a role to play. In automotive design, fluid mechanics has a role to play. So we can say that fluid mechanics, it is one of the most employable foundational subjects. So if you master fluid mechanics, you're mastering one of the most employable foundational subject. And just look at the career pathway. So fluid mechanics is a very important foundational subject, and we have to master it. And this course will definitely help you in mastering fluid mechanics. Software tools overview. Now fluid mechanics today, it is computationally driven. So we make use of software while studying fluid mechanics. So we have Excel. Excel, we make use of Excel like for iterative solutions, friction factor calculation, turbo machinery analysis, like the velocity triangles, pipe network solutions. Now see this Excel, we already know that it is widely accessible and powerful. Excel is a very important tool, and we make use of Excel in fluid mechanics also, study of fluid mechanics. Other tools we use is the CFD software, that is the computational fluid dynamics software. And if we look at some examples of it, we have ANSYS, COMSOL, OpenFOAM, MATLAB, Star CCM Plus, and in the MATLAB, we have PDE toolbox, MATLAB PDE toolbox. Now, these softwares, we have dedicated softwares for computational fluid dynamics, and they are used for solving Navier-Stokes equations, aerodynamic simulations, there's a lift drag, multi-phase flows, and combustion modeling. They are used for combustion modeling. If we talk about programming, now we can, instead of using a software, we can write programs also. So to write programs, we can make use of different languages. Like we can do it in Python. In Python, we have libraries like NumPy, SciPy. We can make use of MATLAB. We can make use of C++, Fortran. There are some legacy codes. So the idea is very clear. If I talk about computational fluid dynamics, so high level careers, they often require computational fluid dynamics with programming expertise. So this is the so like the fluid mechanics of today, of the modern world, wherein we are not at all just bounded by theoretical study of like using integral methods and differential methods, and not, and also not even experimental methods. Rather, we are going one step ahead, and we are studying computational fluid dynamics. Like now, computation is also a core component of fluid mechanics study, wherein we are making use of softwares like Excel, CFD softwares, or programming languages. Okay, so the big picture takeaway. So now, whatever we discussed, if we have to summarize that, so we can say that the fluid mechanics is mathematically deep. Like it has equations, theorems, and calculus in it. It is experimentally grounded, lab work, prototypes, observations. It is computationally powerful, simulations, computational fluid dynamics, modeling. It is industrially essential because we already saw the scope of it. It has scope in aerospace, automotive engineering, energy sector, power generating sectors, oceanography, meteorology, hydrodynamics, and so on. It is environmentally critical. Fluid mechanics has a role to play in climate, study of climates, oceans, pollution, and it is historically rich. Like fluid mechanics is not something very new, but it has got some very good history associated with it, wherein Da Vinci, Bernoulli, Reynolds, we are still using their findings, their equations. So it is historically rich. So fluid mechanics connects theory with the physical world, because the world where we live in, 75% of it is surrounded by water, and 100% of it is surrounded by the air. And almost every engineering system, it interacts with the fluid, and hence the fluid mechanics. So fluid mechanics is a very important foundational subject which connects theory with the physical world. So finally, we completed this lecture. In this lecture, we saw definition of fluid mechanics. What is fluid mechanics? We saw why it is globally important. We saw its interdisciplinary scope. We saw the triad, the integral, the differential, and the experimental methods of studying fluid mechanics. And we also saw the career and computational relevance of fluid mechanics. I hope you got a very good understanding of the concepts which we discussed in this lecture. So do subscribe to our YouTube channel, Scale Up University, for more such interesting lectures and courses. Thanks for watching. Thanks for your time.